I am Dr. Kusumita Kundu, Assistant Professor of Chemistry in SBIST. Today's topic is optical isomerism. It is basically under the stereoisomerism. Stereoisomer is basically two types. One is geometrical isomer and one is optical isomerism. So in optical isomerism, we will first talk about the optical activity. Optical activity. Optically active molecules. How we will find that the molecule is optically active? If the molecule, any molecule, rotates the plane polarized light, rotates the PPL or plane polarized light, be it in positive direction or be it in negative direction, then we can say that the molecule is optically active. Okay. Now, if the molecule is rotating the PPL to a positive direction, then the isomer is known as D isomer or dextrorotator. D isomer or dextrorotator. Okay. And if the molecule rotates the PPL, that is plane polarized light, in the negative direction, that isomer is known as L isomer or liborotator. Liborotator. Okay. So this was D and L isomer. It is basically dependent on the rotation of the PPL, that is plane polarized light. Okay. Now coming to the topic of chirality. Now what is chiral molecule? A chiral molecule is said that if a carbon atom and the attached four substituents, and if the four substituents attached to this carbon atom is different, totally different to each other, then we can say that this carbon atom is a chiral carbon atom. It is a chiral carbon atom. And this chiral carbon atom is denoted as C star. This is denoted as C star. Now we are taking some examples. Right? This is an example of tartaric acid. HOH, HOH. This is an example of tartaric acid. Okay. Now, before we proceed, we need to know that the conditions to be a molecule to be an optically active molecule. If a molecule is optically active, then the molecule should not have any type of symmetry elements. Okay. No symmetry elements should be present in an optically. No symmetry element should be present in optically active molecule. What are the symmetry elements? Basically, there are three types of symmetry elements. One is POS, that is plane of symmetry. Second is COS, that is center of symmetry. And the last one is alternating axis of symmetry. Alternating axis of symmetry. Alternating axis of symmetry. So, in any molecule, if any of this symmetry element present in any molecule, then we can say that the molecule is optically inactive. A molecule to be optically active, there should be no symmetry element present. Okay. Now, coming to the example, tartaric acid. Now, in this case, we can see that there is a POS, plane of symmetry. Okay. That means this form is optically inactive. This form is optically inactive. Okay. Now, this is also a chiral center, this is also a chiral center. Now, if we change the position of hydrogen and hydroxyl groups, what will happen? This is HOH, HO and H. Okay. Now, there is no plane of symmetry. That means this form of tartaric acid is optically active. Okay. This is optically active form. Now, if we draw the mirror image of this molecule, How does it look like? OH, H, OH. Okay. If this molecule is, let's say this is B, then this molecule will be L, because this is exactly the mirror images. Okay. So let's say this is the structure 1, this is structure 2, and this is structure 3. Okay. So structure 2 and 3, they are non-superimposable mirror images. Non-superimposable mirror images. Whereas in structure 1 and 2 and structure 1 and 3, they are neither superimposable nor mirror images. Okay. So structure 1 and 2 and 1 and 3 are known as diastereomers. Diastereomers are those form of the molecule which are neither superimposable nor mirror images. These are called diastereomers. While in case of 2 and 3, they are non-superimposable mirror images to each other. These 2 and 3 are enantiomers of each other. These 2 and 3 are enantiomers of each other. Okay, so this is the basic difference between enantiomers and diastereomers. Okay, so in the next class we will be covering the RS nomenclature. Thank you so much.